First few minutes here are going to be a review of sorts, what we've been doing, some of it. We have this Leibniz notation. Leibniz being the French mathematician who's given credit for along with Newton. Have your paper. Are they? Oh, here it is. And he used a different notation. This is an example. E dx, e to the x equals e to the x, which is notation. He wanted to write out the quotient formula. Well, it's not as compact as Newton notation. Newtonian notation. dx f of x prime of x minus dx x. Oh, myself mixed up here. Dx squared. We've run into some derivatives of trig functions. Derivative of the sine is the cosine. Derivative of the cosine, negative sine. Derivative of the tangent is the secant squared. Once you know these two, you can derive all the others using product and quotient rule, but these three are the most important to kind of have burned into your memory. Derivative of the secant is the secant times the tangent. Derivative of the cotangent is negative cosecant squared, and derivative of the cosecant is negative cosecant times the cotangent. So, okay, this is, this and the other rules, which I'm not writing down, the sum rule and the product rule and the power rule, are most of what we know now. We're going to learn a little more today, but I thought it'd be worth just looking at a couple examples. How's that down here? We can't do that yet. Can we? Oh, yeah, I guess we can. Not everything is going to be trivially simple. Okay, so what's the derivative of f of x? Well, we have a problem here. We don't know what the derivative of f of x plus 1 is. We're going to have later today kind of a direct assault on that, so you don't even have to think about it. But there is something we can do here. We can use our laws of exponents, and we know that this is e to the 1 times e to the x plus 1. And so the derivative is just e to the 1, e to the x. Well, the derivative of 1 is 0. So it just turns out to be e to the x plus 1. That's a simple example. trying to show you something, I guess, obvious about the quotient rule. You might think this would be much easier if we reduce it first, and we're going to do that, but just as kind of a check, it's going to be the derivative of 3x squared plus x cubed times x minus derivative of x, which is 1, times 3x squared plus x cubed all over x squared, right? Derivative of 3x squared plus x cubed. Now we have to use the sum and power rules, so that's 6x plus 3x squared times x minus 3x squared minus x cubed over x squared. 6x squared plus 3x cubed minus 3x squared minus x cubed over x squared. And what do we have in common here? Cube. 6x squared minus 3x squared is 3x squared. 3x cubed minus x cubed is 2x squared. X squared is what? 3 plus 2x. Well, let's see if we end up with the same thing by reducing first. 3x squared plus x cubed over x. X isn't 0, it's 3x plus 3x squared. And so the derivative, using just the power rule and the sum rule, is 3. Oh, I hate when oh, that's just x cubed. What was I doing? Just x squared. Gosh. Plus 2x. There we go. Making little mistakes is okay if you correct them immediately. All right. Few more examples before we move on. You may wonder why I'm wasting time when I have new material over these examples. These kinds of problems are exactly what you're going to have to produce on an exam and your homework. And frankly, they're the mechanics of calculus. You do have to understand what we're doing here. We're finding a function whose values are the slope of the tangent on the original function. But a lot of this is mechanics. A lot of the work here is mechanics. So the only way to really get good at this is practice. So, okay, here we have some problems where we want to find f prime of x and the second double prime, the second derivative. So if f of x equals x squared e to the x, obviously we have to use the product rule. So x squared times the derivative of e to the x plus e to the x times the derivative of x squared is 2x. That's f prime of x. Second derivative, isn't this neat? We already did this, or up here, right? So we can just repeat what we have. X squared dx is 2x e to the x. Now we have to find the derivative of 2x e to the x. So again, 2x times the derivative of e to the x plus e to the x times the derivative of 2x, which is 2. And looks like we can combine these terms. Similar problem. X equals x squared sine of x. Right? Using the product rule, x squared times derivative of the sine is the cosine of x, plus 2x sine of x. Find the second derivative. Well, again, here we're going to use the product rule, and here we're going to use the product rule. So x squared times the derivative of the cosine is the negative sine, plus 2x cosine of x, that's this part. And here we have 2x times the cosine of x plus derivative of 2x, which is 2 times the sine of x. And again, we have some components we could combine. All right. This next one, I'm just going to do the derivative. The function is cosine of x over 1 minus sine of x. I wonder if anyone recognizes that. I think that's some half-angle formula. Memory will fade. That brings up a little digression here. If you are feeling weak in your trig functions, don't just let it go. What are the resources available? I'm just reminding you all that there's I don't remember when it is now. It used to be Tuesday, Thursday at 5. But there are math help sessions that you can find out about, and you could ask Christine in 222 when and where. Some some senior or junior math majors will help you. I have a lecture online that I'm not going to give here because we already did a review at the beginning of the year. It's number 10. You know where my website is. You can look that over. Just some basic information. And then there's, of course, all the online stuff available, Khan Academy or whatever. But you do want to know, I think we might run into an identity here that should be obvious. So, all right, let's go ahead. So we have the derivative of the cosine times 1 minus sine minus the derivative of 1 minus sine of x, which is minus cosine of x times cosine of x, all over 1 minus sine of x squared. Now, okay, minus minus is plus. Let's see what do we have. We have minus sine of x. No. No, we don't. Yeah, there's the x. Minus sine of x times 1 plus sine squared of x plus cosine squared of x. That should, you know, your trig antennas should all be like firing like crazy when you see that. And this is 1 minus sine of x squared. Well, this is just 1.
Is that a good one? Like the one plus sine x? No, not the other one. No, the other one. To your right.
This one?
No,
This one?
no, the one that we bunched together. Like next
Over
to the
here?
first one. Yeah, that one.
Well, it was minus because of the product, minus cosine
Oh,
because, Because what? Because it was, I don't know, let me go back. Derivative of this times this, derivative of this times this. So what's the derivative of 1 minus sine of x? Well, 1 is 0. Derivative of the sine is the cosine, and we've got a negative. That's where this came from. I'm sorry, you will learn to do it faster. I already do it fast, but you should slow me down if something like that sneaks by. All right, so we have, oh, this is going to turn out nice. 1 minus sine of x over 1 minus sine of x squared is just 1 over 1 minus sine of x. With, warnings about, if you had x is pi over 2, and this is 0, and it's undefined. Oh, well, you still have that here, so you don't have to worry. All right. 2 more forms of problems that involve what we're doing here, but are a little more advanced. Is everybody done? Okay.
Just real quick, just on the top very first, no, yeah, that one.
Mhm.
You just square the bottom, and then each derivative of the cosine, and then just take up the square. So it'll be 1 over.
I'm not following you, but are you asking, is there a way to simplify this before you do the derivative? And multiply by 1?
No, just square it, because g of x is squared at the end, right? When you do the product.
Well, you have to square it for the formula.
Yeah.
If you square this now, you have to multiply this by 1 minus sine of x. This is the original function,
Yeah.
right? So if you want, you can multiply this by some form of 1. Now, my guess would be maybe 1 plus sine of x.
Yeah.
Oh, okay. 1 plus sine of x plus sine of x. This will become 1 minus sine squared, which becomes cosine squared, which is going to cancel here. Well, that's, I'm sorry, do that too fast. Want me to do that?
No, I'll just.
Okay, this is cosine squared of x over cosine of x times 1 plus sine of x. And then I can cancel here. So now well, I really haven't helped that much. Now I can find 1 plus derivative of 1 plus sine of x over cosine of x. They still have to use the product. Well, I could use, okay, if I do that, now I have the secant plus the tangent. I can just find the derivative of the secant plus the tangent. There are always other ways, there are often other ways to do it. Is it simpler? If it is, do it. Right?
And if that'll be all right for the.
Yeah. Now, of course, the most important thing is not getting the right answer. The most important thing is knowing what you're doing. So if you make a little mistake, I'll see that when I correct it. But how you get the answer? I mean, if your logic is good, if you're using math, I will never complain about that. All right, back to Grace. Okay, so the next type of problem Usually they'll look simpler, but we might as well make it look a little intimidating. I have this function sine of x plus cosine of x. I want to find an equation for the tangent to this curve at 0, 1. Okay, so there's two parts to this. We want to find the derivative. That's going to tell me the slope of the tangent. And then you have to go back to your algebra 1 and you need to find the equation of the line, given a point and a slope. Now, as a general recommendation, I always think it's good to make sure that this isn't a bogus question. Is this point actually on the curve? So what we want to know is if 1 equals sine of 0 plus cosine of 0. Sine of 0 is 0, cosine of 0 is 1. Okay. Because if it's not, you can't really answer the question properly. Okay, so we want to find the derivative. Derivative of the sine is the cosine. Derivative of the cosine is the negative sine. And we want to find, actually going to use a derivative. We want to find the derivative at 0. Cosine at 0 is 1. Sine is 0. So this is our slope. Now, if you happen to know the slope point form, you can just write it down. I like to write it down. Y equals mx plus b. I remember that from high school. N is 1, so y equals x plus b. And then I plug in my point, 0, 1 here. Y equals 0 plus b, and I discover b equals 1. So the equation of the line is y equals x plus 1. That's the answer. It's kind of an obvious thing to do once you know how to find a derivative. Give me the equation of the tangent at some point. All right. The next problem is, I want to show you, is it's kind of a trick to it that maybe you haven't seen. And it's all, it amounts to just remembering this trick. The problem is, what is the sine of 7x over x, the limit as x goes to 0 equal to? So, all we know at this point is that from our last class is the limit as x approaches 0 of sine of x over x equals 1. So, I guess we could guess 1, but that would be a bad guess. We could graph it and look at the graph and see it's not 1. But we want some way to do this. So the whole trick here is you just say, well, wait a minute. What about substituting u equals 7x or x equals u over 7? What does that do for us? Well, if x goes to 0, and u is 7 times x, what is u going to? You have to think that through. Okay. x is going to 0. What is 7x going to? It's going to 0. Good. All right. We have the sine of u. And x is u over 7, or 7 sine u over u. The limit as u goes to 0. Well, we know what this is. This is 1, so it must go to 7. That's the trick. All right. So this is phase 1 of the class. Anyone have any questions about this? Just a few problems. I'm gonna go backwards, and I'm gonna explain why. My apologies to all the students here who really understand composition of functions, but the word I got back from my grader was that people had problems with composition of functions, and I understand that. It's just like doing derivatives. It takes a little practice to kind of think in an abstract way. So we're going to do a few examples here. I'll do one here. We have f of x equals e to the x, and g of x equals x over x plus 1. And the first problem is, what is f of g of x, which we could also write f circle g of x. So when you look at this, you want to, this is the way I think of it. You want kind of a visual way to think about how this works. And we're taking g, that's this thing here, and we're plugging it into f of x. So this is f of x, and this is the x in f of x. So what we're doing is we're plugging this in here. So what we get here is e to the x over x plus 1. If you have trouble with composition, try and let that sink in. This is my g of x, which is in here, right? I'm going to grab it, and pull it over, and stick it wherever there's an x. All right. Let's try the other way. Let's try g of f of x. Oh, now I'm going to take f of x, and I'm going to stick it in here to this x, and it gets reproduced here and here. So it becomes e to the x over e to the x plus 1. Clearly, this is not a commutative operation, generally. Does anyone remember when it is a commutative operation? F of g is equal to g of f. Anyone remember? Okay, you should try and remember. When they're inverse functions, and in fact, in that case, they'll always be equal to x. All right. Why don't you all take a minute? I hope you have some scrap paper around. And let f of x equals square root of x plus 1. And g of x equals x squared. And let's find both of these, f of g of x and g of f of x. Yes. I got your question. reason I'm doing this now is, as you'll find out in about 10 minutes, we're going to do something called the chain rule. And if you don't understand composition of functions, you're going to trip over the chain. So yes, there will be problems where you need this. They won't be this won't be the form of the problem, but this will be like part of the problem. In a way.
The question was just, I was asking, would we be doing problems in any class, or would we, a given problem that we were doing and we would check over our answers?
Okay, I misunderstood the question. You're asking, will we be giving problems in class? Well, sometimes I just did.
But in more complex, that would be a little more.
This coming, yeah. Okay, someone want to tell me what f of g of x is? Anyone? Yes?
Okay, so the square root and x squared plus 1.
So we took g of x, we plugged it in here, and it goes there. Yeah, looks good. Okay. Someone else tell me what g of f of x is? Yeah?
X plus 1.
Yes, but I'm going to do an intermediate step, right? It's square root of x plus 1 squared, which you just reduce to x plus 1, yes. Anybody have a question how we got that? These are real basic. Maybe this is enough. We don't always have a mixed kind of function. Sometimes it's just hard work. F of x equals x squared. This is just going to be polynomials. And g of x equals x plus 1 squared. So again, with practice, you kind of, you just, it's like substitution. You just substitute the right thing in the right place. Here, we're going to substitute x plus 1 squared, g of x, into here. So we get x plus 1 squared plus 4 x plus 1 squared plus 3. And then there's plenty of work here to simplify, but that's not necessary. You often find with a problem like this in calculus that there's no reason to simplify it, because really the question is, what's f of g of x prime at 0? So you just look, oh, it's 1 plus 4 plus 3. Or better yet, minus 1. It's just 3. So, all right. You're feeling weak on composition? I encourage you to come see me, come see the math tutors, math department, get help. You're going to need to be able to do this. And it's okay to do it slowly and carefully, but you do need to do it, need to know how to do this accurately. All right. The chain rule. Section 3.4 in Stewart. And we will get to why it's called the chain rule in a bit. So we might have functions x is square root of x, where we know the derivative. And g of x, where we know the derivative of x. But we might be tasked with finding derivative of f of g of x. And this is where the chain rule comes in. Chain rule says that derivative of f of g of x is the derivative of f of x at g of x. I guess I don't want those brackets. Derivative of f of x at g of x times the derivative of g of x. I feel like I need to repeat this. The derivative of the composition of these two functions is just the derivative of f of x at g of x times the derivative of g of x. So what does that look like? Well, here we know the derivative of f of x is 1 over 2 squared root x. So g of x at the derivative is just 1 over 2 times the square root of 2 of x squared plus 1. But we have to have the last part on g of x. So this turns out to be x over square root x squared plus 1. That's the derivative of this composition. So you don't actually have to form the composition if you know the derivatives.
The two cancel, that's why it's not in the final product.
I'm sorry?
The two x's it cancel? That's why it's not in the final product.
Saying the
It's-
2 and the 2x.
The 2's cancel.
Yeah.
Yeah,
Just making sure.
yeah. I'm sorry.
No worries.
2.5. Multiplied together is 1. Okay. Why do we call this the chain rule? Well, if we write this in Leibniz notation, we would write it this way: dy dx equals dy du du dx, where what's u here? U is what is u here? Where we have y equals f of u, and u is equal to g of x. There are going to be circumstances where it's going to be really, really convenient to use this form. But why we call this a chain rule is you can extend this. If we wanted f of g of h of x, right? The Newtonian version would be f prime at g of h of x times g prime at h of x times h prime of x. But in the Leibniz notation, if we just say this is g of v and v is h of x, and we can just write this dx equals dy du dv dx. So you can just, you can keep doing this, chaining it if you have composition. Now, I think it's important for me to emphasize something I've said before. This is no dy du or dy dx is notation. These aren't fractions. But it is useful to remember it, that, well, it looks like, you kind of cancel these and get dy dx. That's fine to remember it. Just be aware this is notation. It's not an actual fraction. All right. So the next thing I might do in class is I might want to prove this for you, the chain rule. I think that would be abusive. You wouldn't get much out of it. It wouldn't be rigorous anyway. But at least I want to make it seem plausible. So let's do some examples where we could use the chain rule, but we don't have to, and see what comes out of it. So if f of x is x, and g of x is x squared, we want to know what f of g of x is. Well, we want to know what the derivative is. Well, you can see right away that this is just x squared. Now, let's use the chain rule. It says derivative of f of g of x is f prime at g of x times g prime of x. So we have to figure out what the derivatives are here. Derivative of f of x is 1, and the derivative of g of x is 2x. Well, the derivative at g of x, since it's a constant function, is just 1, and this is 2x. But we know that the derivative of x squared is 2x, so at least for a super simple example, it works. I think I'm going to leave that there. If you're interested, you can look in the book. I think they have a derivation. As I say, it's not rigorous, but at least it give you more mechanics. Any questions so far about the chain rule? We're going to do some examples here to kind of give you a feel for what you can do with this. This is unless like me, you're kind of dyslexic and you have trouble with the quotient rule. Where's the minus go? Which way? This is the hardest rule to deal with in calculus. You're going to want to do the homework carefully, practice it, make sure you feel comfortable with it. If you don't, definitely, bring questions into class about it. Even though stating it is straightforward, when you start looking at some complicated functions, sometimes, even I look at something and I have to think about it for a while. How does the chain rule apply? All right, let's start with the problem we did before. Well, we've seen this before. X is the square root of x. G of x is x squared plus 1. So the derivative of f of x is 1 over 2 square root of x. In case it's not obvious, this is x to the 1/2, and I can use the power rule. 1/2 x to the 1 minus 1/2, which is negative 1/2. So that's how I get 1 over square root of x. A derivative of g of x is 2x. So my chain rule tells me this is going to be the derivative of f of x at g of x. So 1 over 2 square root of what? 2x. You know, it's funny, in the privacy of my home when I'm doing math, you know, usually I feel pretty confident. But standing up here on the board, I know, you know, my brain and my hands, you know, the left brain and the right brain get out of sync. But something wakes up in me and says, wait a minute. And I don't know why, but I did something wrong here. Anyone see what I did wrong? Okay, then you're paying attention. Good. Right, you can hold on to that. I did something wrong. Yeah. Yeah. No, it's not g prime of x that gets plugged in here. It's g of x. All right. You don't have to be shy, Mr. Schoenbrun, because I will make mistakes. I always have to catch them. Well, too bad. Okay, where am I? F prime at g of x. There's f prime, there's g of x, right? Times g prime of x. So we get x over square root of x squared plus 1. Let's do something a little more exotic looking. F of x equals x squared, and g of x equals sine of x. So really what I'm saying is what am I saying? I'm saying f of g of x is what? Sine of x squared. I probably wouldn't give you this. I'd probably just say, what's the derivative of sine of x squared? Which is, you know, we write that as sine squared of x. Well, okay. Derivative of f of x is 2x. Derivative of g of x here is cosine of x. So f prime at g of x times g prime of x is what? F prime, that's 2x, 2 times x at g of x. So 2 sine of x times g prime, which is cosine of x. Anyone recognize 2 sine of x, cosine of x? It's a trig identity. Be good to recognize. This is sine of 2x. There's something more here. I'm seeing it, but I feel it. There's something more here of interest. No? Okay, I went through all this. I want to do this a little differently. I mean, more compactly. I want to find the derivative of sine squared of x. So in my head, I think power rule, like x squared, is 2 sine of x. But I'm not done. I have to find the derivative in here. Okay, that's kind of the short version. I'll show you some examples of doing that. It's not really a shortcut, it's just not writing it all out. I mean, I'm not dividing this clearly into a composition yet. I'm just kind of, I don't know how to describe it. Let's try another example. No, good. Beautiful segue. Here's something that looks intimidating. E, the square root, x cubed plus 2x plus 1. And I want to find the derivative of that. Now, the long way is to say, well, we've got e to g of x, where g of x is square root of x cubed plus 2x plus 1. Oh, but wait a minute. G of x is equal to the square root of h of x, where h of x is x cubed plus 2x plus 1. So this is f of x. So I could try and break it down that way and then apply the chain rule. Or you kind of do this shortcut. I look at this and I say, well, derivative of f of x is what? E to the something, e to the x, is e to that something. Times the derivative of this. This is the square root of something. Well, that's 1 over 2 times square root x cubed plus 2x plus 1. But the chain rule requires I multiply again by the derivative here, which is easy, 3x squared plus 2. All right, we'll come back to that after the break. I mean, it can be that, you know, once you get the rhythm down, it can be that easy. You just have to be careful. And I guess you have to see this as a composition of a composition here. E to something, that something is a square root of something, right? And, you know, this could be something else that you have to break down, add another layer to the chain. All right, again, take a break. I'll be back in a few minutes.
So
I got you on my stack. Up here.
And the triangle. Like, they're on your mind. You know that.
Okay, yes.
Where did you get the 1 over 2 times? Like, why is it 1 over 2?
I don't know if this helps.
So I understand where that comes from. Where did you, if that's the case, then where did you get
So-
the square root of x?
So this is like f at g.
Okay.
I mean, this is the derivative of f at g. It's easy because e to the x is e to the x. So this is the.
Oh, so we're just assuming that g of x was
This.
x cubed plus
Square root of.
square root of,
Yeah.
and so f of x was,
Was this times the derivative of this. The derivative of this is
so, okay,
this
so
at
that's f
h of x, and now I have to multiply it by the derivative of h of x.
So the middle one is the derivative of g of x.
I didn't hear you right, but I think that's right. It's 1 over 2 squared x. Now, there's no shame in writing all this out, right? Especially at the beginning when you're learning. As time goes on, you get to where you can just kind of rattle things off.
Do you mind walking through the composite then? I feel like I know what you were trying to say, but I'm still kind of iffy on how I got it, so.
And that's a reasonable feeling at this point. I just showed this to you. I've been doing it for 40 years. So, sure.
So f of x is e to the square root.
Let's do a series of related simpler problems. Derivative of e to the x. Well, that's e to the x. Derivative of e to the square root of x. That's e to the square root of x times the derivative.
1 over.
Yeah. And then the last step is just this one. Instead of x, we have this ugly thing, plus plus. And we just have to finish it off by putting in 3x squared plus 2. Chain them together, yes.
Is a problem like that going to be on our exam? Okay.
Depends on what you mean like that. A problem like that, a chain rule problem? Yes.
To that extent?
Well, that would probably be a little mean, wouldn't it? Because you're in an exam and you're sweating,
Exactly.
your whole career is on the line.
Exactly.
Yeah, that would be kind of mean. I probably wouldn't put something like that on the exam.
Thank you.
But I would hope, in the privacy of your home or dorm, if you see a problem like that, spend time calmly going through it. There will be chain rule problems, but hopefully, I mean, I could make something, this could be the cosine of the square root of the, it could go on and on. And you have the tools to do it, but that's not, the purpose of an exam is not to see if, you're ready to be some kind of, you know, high-flying acrobat, you know, in front of an audience with no net,
Got it.
right? So,
Thank you.
okay. So, I have from another text in my notes, a whole list of good chain rule problems. I'm going to do a couple of them. You're encouraged. You feel enthusiastic about this. I know sometimes you go home and, oh, glad that math class is over. Glad this math assignment is over. I know that, you know, it's part procrastination and part avoidance. But, you know, if you gather a little enthusiasm, you're also welcome to, like, one of these, you don't get it at all, you can bring it into class, even though I didn't assign it. So, again, this is in my notes online. If you need to know where that is, you can always email me. I want to do a couple of them, or let you do a couple of them. We'll start with, these are just functions and I want to find the derivative. Excuse me. So give that a try. Actually, I just made that one up. It's not, it says here. Doesn't it? Now, I think we're close here. Clearly, like, multiplying this out, you get a polynomial and use the sum and power rule. That would be somewhat painful. So the chain rule really helps a lot here, right? Because this is u to the sixth, where u equals 1 minus 2x. Okay. Someone want to take a guess here? Not a guess. Yes.
Negative 12x to the fifth.
To the fifth. Okay. Okay. So there's an error here, and you're probably not the only one making this error. You can't just, I mean, this is like u.
Or is it plus 1?
It's not that it's plus, it's, all right. Anyone want to have something different? Yeah?
Negative 12 times 1 minus 2x to the fifth.
Negative 12 times 1 minus 2x to the fifth. That looks like it's got possibilities. I haven't done it yet, so So here we go. So this is like some function. So I'm using the power rule here. So kind of bring this over. 6, 1 minus 2x, the fifth, times now the chain rule thing pops in, times the derivative of this, which is -2. So it's -12 times this, so exactly correct. Did you see how I did that? Yeah. Okay. Let's push this step further. Oh, this is ugly. All right. It's got an ugly part to it. That's the ugly part. Okay. Have a minus sign. Have a go at that for a minute. I'm going to be kind. I'm going to rewrite this. This is x squared minus x to the minus 2. I think that'll make it easier. Which is something you should do if it makes it easier to rewrite something like that. Remember, we're not looking for some beautiful simplification here that's available. I don't care about that. I just want an expression for the derivative. Anybody want to take a shot? I want to come back to this. I want to just throw up another problem, which there's in number theory, I think, there's something called the law of large numbers. And I don't remember what it is. Doesn't matter. But I think there's a law of scary large numbers, right? Scary large numbers. Well, it's not. This doesn't matter what this number is. It's an n. Make it easier. It's just 100 times x squared minus 1 to the 100 minus 199. That's power rule. And then I just have to multiply by the derivative here. I mention this because, yeah, this looks scary because, you know, math is scary. But this is why you have to be a little bit brave around math problems. I learned everything, well, maybe not yet. I learned it, practiced it, I can do it. It can't be all that bad. So what do we got here? Well, again, there's some function here. I'm going to use the power rule. Squared. And now I just have to find the derivative here. Well, this is 2x minus, oh, it's still the power rule, minus 2 x to the minus 3. Now this just becomes plus. That's it. All right, well, again, there's a homework assignment, but, it's like if you go out for the track team, the coach makes you go run 2 miles. I think I really want to win the state championship, so I'm going to go out on my own. You can look these up, and these are good problems here, and I'm happy to field questions on them during the class or otherwise. All right. So, So now that we know the chain rule, there's something that's new, and I think first it seems a little tricky, but it's really kind of beautiful that you can do this. I guess I should give it a name. It's called implicit differentiation. And it's section 3.5. Stewart. So, first thing is I want to help out with what this vocabulary means. If I have some function, it doesn't really matter, x over cosine of x squared plus 3, whatever. My function here is explicitly defined. This function is, you know how to find x. There's no, right? You just plug in x and you get your value. Sometimes we don't have that. Also, this is a function. Sometimes we don't even have a function. So let's take a nostalgic journey back to, I bet some of you haven't seen this, time in the past when your math teachers, this terrible drawing, told you about something called an ellipse. Ellipses are kind of cool. You have the sun here, you have the Earth. Approximately, the Earth goes around the sun in an ellipse. Kind of speeds up because of gravity, and then gets flung out, and then goes slow, and it comes back in. And you might have learned that there's a general form of an ellipse that's centered at 0, which is x squared over a squared plus y squared over b squared equals 1, where a is the semi-major axis, b is the semi-minor axis. So you might have something defined this way. There's no, what's the function? There's no function. It's not a function, right? It fails the vertical line test. But it is the case that at every point there's a tangent. So it'd be nice to know what the derivative is there. And, well, calculus hasn't told us how to do that yet. So, let me put up an even more challenging looking expression. I have some curve defined this way. And I want to know for some point on this curve, I want to know what the slope is, and then maybe I want to find the line, equation of that line. And I really don't know what this looks like. I could graph it and see. But it's clear I'm not going to be able to get this as an explicit function, right? If I pick an x, I can find y. If I pick a y, I can find x. But I can't describe this as a function, or I probably can't. Or even if I could, it's kind of messy. So we have a technique called implicit differentiation that works wonders. As long as you know the chain rule, and you can be a little open-minded. So what we're going to do here is we're going to think of y as a function of x. And we're just going to use what we know about derivatives, and we're going to try and find the derivative of this. We don't have to know what y is explicitly. We just know it's some function of x. So here's how we go about it. First, on this side, I'm going to use the sum rule, and here's the power rule. Derivative of x cubed is 3. Here, well, this is some function, like f of x. So it's 3 times function squared. Chain rule times the derivative. I'm just going to write it y prime. Okay, that's the whole thing right there. So I'm just going to go back. I'm finding the derivative with respect to x. So this is just 3x squared. We all know how to do that. This is some function of x. We don't know what it is. We don't need to. We know from the chain rule it's going to be 3y squared times the derivative of y. That's what the chain rule tells us. That's 90% of this. You get that, you're gonna find the rest easy. Okay. How about 6xy? Well, okay, I can use the product rule. I'll take out the constant, just gonna get in the way. So we want the derivative of x times y. So that's the derivative of x, which is 1 times y, plus x times the derivative of y. All right. Now let's do some algebra here. X squared is 3y squared times y prime equals 6y plus 6xy prime. All right, now what I want out of this is I want to know what y prime is. So let's put the y primes on one side and everything else on the other. Move the 6y over here. Move this over here. And I'll factor out the y prime. And still have this. Now I can divide by this, and lo and behold, I get y prime equals 3x squared minus 6y over 6x minus 3y squared. Oh boy. So even though I don't know y explicitly, if I have an x and a y, I can find the tangent to that curve at that point. That's just, it's just marvelous. This is, I implicitly can find the derivative. So this is called implicit differentiation. It's just a nice technique. I guess we should. All right, so let's do the next part of this problem, which I didn't really describe. So, find the equation of the tangent at 3, 3. All right. Now, as I suggested in an earlier find the equation of the tangent problem, one wants to be a little skeptical here. We want to make sure this point is actually on the curve, so let's do that. So 3 cubed plus 3 cubed equals 6, 3 times 3. This is 27 plus 27 is 54. This is 9 times 6 is 54. Oh, good. So now I want to find f prime at 3, 3. Well, it's 3 times x squared minus 6 times y over 6x minus 3 y squared. What we got here? 27 minus 18 over 18 minus, that's too easy, that's minus 1. So here we have, this is our slope m, right? And again, you can use the point slope form to find it, or you can do it the long way. Y equals mx plus b, so y equals negative x plus b, 3 equals minus 3 plus b, or b equals 6. So we get y equals negative x plus 6, and that's our tangent. I'm gonna do one more implicit. This will start over here. This again has the property of looking intimidating, but it's straightforward. It's just, you're still staring at that. I want to let you sort that if you need to. Everybody okay? You want to find y prime if we have sine of x plus y equals y squared cosine of x. It's the same strategy. We're going to find the derivative with respect to x. knowing that y is some function of x. So using the chain rule, derivative of the sine is cosine of x plus y times the derivative of x plus y, which is 1 plus, we don't know, but that's what we're looking for, y prime. That's equal to, well, here we're going to need to use the product rule. Derivative of y squared, that's 2y, the chain rule, times y prime, times cosine of x, plus y squared times the derivative of the cosine, which is negative sine. At this point, we have some algebra to do, but mainly we want to isolate the y primes and solve for it. So we have cosine of x plus y times 1 plus y prime is y prime times cosine of x plus y equals 2y, y prime, cosine of x, minus y squared, sine of x. And we want to put these two on the same side, and everything else over there. So we have y prime cosine of x plus y minus 2y, y prime cosine of x equals, two minuses here, minus y prime, no, minus cosine of x plus y minus y squared sine of x. We factor out the y prime. Equals this, same thing. And we divide through. And we'll get y prime equals negative cosine of x plus y. Gosh, this is ugly and scary. It's just, once you know how to do the strategy, the technique, it's just algebra. Cosine of x plus y minus 2y cosine of x. So if we were asked to find the slope at, say, 0, 0, that would be pretty easy. Cosine of 0 is 1, so minus 1 minus 0 over 1 minus 0. It's negative 1. I'm going to let you try this next problem. We've kind of done it twice already. We did it with geometry. We did it by making the equation of the circle a function. We limited its domain. I have x squared plus y squared equals 1. We should find the derivative using implicit differentiation. Give that a try. All right, does anyone have a prime equals? Okay. You see, you're showing
I got one.
you're showing what people need. They need to be praised, right? You got one? This one? Okay, let's
But that's what I got.
let's just, apply, no offense, the smell test. Got a circle, radius 1. The slope can't be 1 everywhere, so you did something mechanically that didn't work right. But that's okay. You're the only brave person here. You're gonna ace the exam because of that. All right, let's try this. 2x, that part was 18. 2y times y prime equals, what's the derivative of 1? 0. Okay, so 2y, y prime equals negative 2x. So y prime equals negative 2x over 2y, or negative x over y. It's not that hard. If I were to solve for y and limit my domain, so it's 1 minus x squared, this would be minus x over square root of 1 minus x squared, which is exactly the same answer we got on the first day, and then when we repeated this, I think we did it with the product rule, quotient rule, but in a way it's kind of a lot easier and it's a lot more elegant looking answer, except that we don't have it explicitly, we have it implicitly. So, all right. There's one more. One more we can try. Should be pretty quick. Just as with the chain rule, if you look at the back of my notes for today, I have a whole page of problems from another book that are good. You want to practice, get your implicit differentiation muscles working. Y squared equals 4x. That would be some kind of sideways parabola. Just checking missing students George, Renee, Maya, Kwasi, Arian, Monserrat, and Lisa. Anybody have a quick answer? For the bell rings? Yes.
I had 4 minus 2y.
I'm sorry, 4?
Yeah, if I did it.
No, just say it loud. Say
Oh yeah, 4 minus 2y.
minus 2y. Okay. Does anyone else get that? Yes? 2 over 1?
Y.
Or y? Okay. I don't know the answer. Let's give it a try. 2y, or y squared is 2y times y prime equals 4. Oh, y prime equals, yeah, it looks like the second, okay, somehow you have the right numbers, but you got them mixed up somewhere.
You, instead of dividing,
Yeah.
because 2y times y prime is multiplication, when you move 2y over, it needs to be division.
Yeah, yeah.
Instead of subtraction.
Yeah, that's right. When we want to separate y prime, we just divide. Okay, I guess everyone's decided to clap their hands. One more minute, I'll get it back someday.